carnitine can also cross through the membrane. Don't forget that carnitine can pass through the mitochondrial membrane. So let's review. The mitochondrial membrane is permeable to carnitine, citrate, malate, and pyruvate. Okay, here we're looking at regulation of fatty acid synthesis. Here's ACC, and so if it's active, we're going to push through to create fatty acids. If it's inactive, we're not going to push through to make fatty acids. So a low energy state, we would expect to disable a high energy requiring pathway. And if we're high energy, why not create some fatty acids? Alright, so here we're going to look at some fatty acids. And so here we have 16 carbon, 18 carbon, and then we're going to start desaturating or adding double bonds. I drew a line here to represent that all the fatty acids below this line are essential fatty acids, which means we cannot create these ourselves, and we have to get them from our diet. We actually get them from plants because plants have these desaturase enzymes that allow them to add double bonds. And so what is the name of the last fatty acid that we are able to produce? That would be oleate. So that would be a good one to remember, as well as linoleate. And then arachidonate down here, I put a box around that because this is going to also be kind of an important molecule, important fatty acid. And so this is showing one of the desaturase enzymes that plants contain. And so you're going from an 18 semicolon 1 to a 2 to a 3. We're adding double bonds. Let's take a closer look at arachidonate. Okay, so we saw this back in the lipids chapter. I think it was chapter 10. And we saw that arachidonate, which is the 24 fatty acid, so we had this in a triacylglycerol, and we used a phospholipase to cleave it out, and it can be used as a precursor for prostaglandins, thromboxanes, and leukotrienes. And we learned that NSAIDs would inhibit prostaglandins and thromboxanes. And what we're going to do is we're going to look at this reaction a little bit closer, a little bit more in depth. And so first we're going to look at, and we can categorize these in two different ways. Okay, if we go the pathway to create prostaglandins and thromboxanes, that's going to be called a cyclic pathway. And if we go the pathway to create a leukotriene, that's called a linear pathway. And so this is the cyclic pathway. We start with arachidonate, and we're going to learn the name of the enzyme that we use. The enzyme is called the COX enzyme, and we're going to make prostaglandins and thromboxanes. And note that aspirin and ibuprofen are going to inhibit the production of prostaglandins. And so prostaglandins are important in contraction of smooth muscle during labor. That's why women who are pregnant should not take ibuprofen or aspirin, because it prevents those necessary contractions during labor, prevents the production of prostaglandins. And so the COX enzyme, he has two activities. He's got a cyclooxygenase activity, where he's going to add this cyclic oxygen structure, and then he has a peroxidase activity, where he cleaves one of these oxygens off right here. And the next pathway we're going to look at is the linear pathway. I should say linear. And so note that this pathway does not use a COX enzyme. It uses a different enzyme that still uses oxygen, but we call it a lipoxygenase. And so this is called a linear pathway because look at arachidonate. It's linear. And then the cyclic pathway, arachidonate is cyclized. And so this one is not inhibited by NSAIDs, and we're going to produce leukotrienes. Alright, so this slide is kind of intimidating to look at, but let's just focus on this reaction. So when we were learning about beta oxidation, we wanted to cleave the tag into a fatty acid so that we could then do beta oxidation. Well, if we can do that forward reaction, shouldn't we be able to do the reverse reaction? And so this slide is focusing on the reverse reaction, taking glycerol to tags. But we'll note that it's not a one-step reaction. It's a two-step reaction where we're going to take glycerol to phosphatidic acid and then to triacylglycerol. And so this slide is strictly showing the movement of glycerol down to phosphatidic acid. So right here, let me zoom in on this. Sorry about that. Okay, so this is probably easier to see now. So we have, so hopefully you've been following in your book, so it wasn't too bad. But here we have glycerol, and we move to phosphatidic acid right down here. Do you guys remember where we saw phosphatidic acid? It was the precursor to all glycerophospholipids, which are found in the plasma membrane. And so it's two fatty acids with one polar head group, two fatty acids with a polar head group. Note in this slide that taking glycerol and then moving down and then back up to glucose, we've already seen that pathway. And so that was the breakdown of glycerol on page 650. And remember, that only gives us 5% of the energy of in a tag, but the fatty acid has 95%. And so we can take glycerol 3-phosphate, and then we can convert that into one of the intermediates for glycolysis to create glucose. And so let's move to the next slide, and we're going to look at this a little bit more in depth. Okay, so you'll find in biochemistry that one of the hardest parts is just keeping track of what everything breaks down into and what pathway is going to be used. And so I've broken this down into 4 categories. So let's identify where beta oxidation is occurring. So we take the tag to the fatty acid, we make fatty acyl-CoA, we'll do beta oxidation, and we'll create acetyl-CoA. Now let's do this reverse reaction where we want to make a tag. And so this, we'll find, is actually a 2-step reaction where we will make phosphatidic acid and then we'll make a tag. Note that I put glycerol 3-phosphate right here. So let's go back to the previous slide and note that with glycerol, the common intermediate that we'll use to make phosphatidic acid is glycerol 3-phosphate. And that can be, and so that's the pathway to make tags. Now let's look at glyceroneogenesis, or the creation of glycerol. That would be taking tags this way. And then gluconeogenesis is going to occur when we break glycerol into glycerol 3-phosphate and then convert that into DHAP, dihydroxyacetone phosphate. That's one of the intermediates in glycolysis, and then to glucose. And also note glyceroneogenesis, if you have that intermediate in glycolysis, you can just convert it to glycerol 3-phosphate and then up to glycerol. Okay, and so this is just taking a slide from chapter 17 showing the breakdown of glycerol. And so this is just to remind you that you have seen this before. And so here's DHAP, or dihydroxyacetone phosphate. So that can be passed into the glycolysis, or you can use it to create glycerol if you move it up. Okay, so we've just taken glycerol and converted it to phosphatidic acid. We now have 2 choices. So let's go back to our flow chart and look at what our 2 choices are. So we took glycerol to phosphatidic acid. Our 2 choices are we can make a tag or we can make a glycerophospholipid. Knowing the structure of these molecules really makes this a lot easier to remember. Because phosphatidic acid, if you remember, is the precursor to glycerophospholipids. So let's go look at its structure. I mean, it looks a lot like a tag, doesn't it? If we wanted to make a tag, all we'd have to do is remove the phosphate and add another fatty acid. If we wanted to make any number of glycerophospholipids, we just have to attach the head group. And so those are our two choices. Okay, this is showing the tag cycle. The tag cycle says that 75% of all the tags released from all of the 75% of all the fatty acids released from tags. So here we go. We have a tag. We release fatty acids into the bloodstream, and 75% of those are just going to be repackaged back into tags. And so this is a futile cycle. So we have the fatty acids. They're just repackaged back into tags, and the function is not well understood. Okay, this is showing glyceroneogenesis, and the most important guy is glycerol 3-phosphate. And so notice that this is kind of like a shortened version of gluconeogenesis. We're going towards making that sugar, but then look, we've got DHAP. So let's go back to the flow chart. And so we have DHAP right here, and we're going to use that to make glycerol 3-phosphate. So we have dihydroxyacetone phosphate, and we can use that to make glycerol. And then we divert gluconeogenesis towards glyceroneogenesis. And then we can take glycerol 3-phosphate and we can use it for tag synthesis. So how does that happen? Let's just go back to the flow chart and look. Glycerol 3-phosphate. How can that go to tags? Well, we just keep moving to make phosphatidic acid, and then we can make a tag by just adding another fatty acid. Okay, this is showing the regulation of glyceroneogenesis. And so this enzyme PEPCK, or PEP carboxykinase, we saw in, I think it was the second step of glyceroneogenesis. And if you activate, I'll start with inhibit. If you inhibit or turn down PEPCK, you're going to decrease the concentration of glycerol 3-phosphate, and you're going to turn down glyceroneogenesis. If you activate PEPCK, you're going to have a high concentration of glycerol 3-phosphate, and so you won't have any problem running that reverse reaction towards a tag. Note that you have two tissues, adipose and liver, and you get a different response in both tissues. Okay, this is again showing the regulation of glyceroneogenesis. This is with a diabetic, so this is diabetic tissue, and you're going to want to know this name. I can't even pronounce it. Diazoledinin something owns. And so this is a diabetes drug. It's used to increase glyceroneogenesis, which would make a high concentration of glycerol 3-phosphate. And so you won't have any problem converting that into tags. And what's going to happen is you're going to reduce the amount of fatty acid flux. So you reduce the amount of fatty acids, and somehow that increases a diabetic's sensitivity to insulin. You want to know this, so know what these guys are: diabetes medicine, and they increase glyceroneogenesis. Don't worry about the structures. Okay, this is showing two different ways to make glycerophospholipids. And so let's just go back to the flow chart. So really, I should have drawn two arrows going down here, because there's two ways to make glycerophospholipids. And so let's look at the two different ways. So there's strategy 1 and strategy 2. We're going to introduce this new guy called CDP-DAG. And so the CDP just represents a nucleotide. And so we have cytosine right here. So that's the CDP diphosphate. And so we saw another situation where we used a nucleotide to activate something. That was with UDP, glucose, and glycogen synthesis. And so, but this time it's CDP, it's not UDP, so this is CDP-DAG. And so we can attach CDP-DAG to the triacylglycerol first, or we can attach CDP-DAG to the polar head group first. And so do you see the difference here? You're attaching CDP-DAG to the tag first. Here you attach it to the head group first. But the result is the same, that we have our glycerol phospholipid. Alright, so what strategy would this be? So we've attached our CDP-DAG first, and then we're attaching everything else. So we attach the CDP-DAG to the tag first, so that would be strategy 1. And that's the end of the chapter for now.